Hello and welcome back for this. We're still in lesson 2.2. Pardon me, lesson 3.2, chapter 3.2. We're looking at measures of spread. And we had just learned about variance and standard deviation. And now I'd like to extend that to grouped data. So if we go back to the example we looked at in chapter 3.1 on finding the weighted mean, we were talking about hours that teenagers spend on video games. We had grouped that data into these classes. And so there were 3 teenagers that spent between 0 and 3.5 hours on video games. And so with group data, we learned that we have to have midpoints. So here are the midpoints, and here are the number of teenagers. And in Desmos, we put these into, say, X1, Y1. And then we multiply these midpoints in the frequencies into this column here. But now we're going to learn how to use this, but not just get the weighted mean, but get the weighted standard deviation. Now, in your notes, I have a screenshot from Desmos showing you exactly how to do this, because you're not going to ever have to do this by hand. And so I'm going to show you what your note should look like. Your note should look like this. So I'm having you put your data into X1. These are going to be your midpoints or data values, and then your frequencies here in Y1. And then this is the calculation. Now there is a saved Desmos calculation for this in Canvas as well. So you can just click on there and then just use this formula, but just make sure you change your X and Y columns to the number that's in your data set. So if you want to practice with this data here, you could put these X's into X1, these values into Y1, and then use this calculation to make sure that you get the right answer here. So let's go ahead and look at this data from the number of hours that teenagers spend on video games. Okay, so if we go to my Desmos here, you can see I already have that grouped data in, and you don't even need to have this third column, because just doing the command down here tells it what to do. And so our grouped standard deviation is 4.98. Then if you look at the next set of data on the next page, it is going back to another example we did in 3.1 over the grades. And I then put that data as well into Desmos here, using our midpoints and our frequencies. And again, we put that in, and we have our weighted standard deviation here of 11.06. So the last measure of variation that I'd like to talk about in this lesson 3.2 is called the coefficient of variation. And you may have noticed that comparing our mean to our standard deviation, sometimes our standard deviation is quite large, and we want to take note of that. So the coefficient of variation, denoted as C-var, is the standard deviation divided by the mean. It is the proportion of standard deviation is of the mean. The result is expressed as a percentage. Ideally, you want this to be low. When the C-var is high, it tells us that our data is very spread out, while our standard deviation is too large and it's too close to the mean. So let's look at an example here. It says the average age of the accountants at Three Rivers Corporation is 26 years with a standard deviation of 6. The average salary of the accountants is $31,000 with a standard deviation of 4,000. Compare the variations of age and income using the respective coefficient of variation. So let's look at the C-var for age. And that would be the sigma divided by the mean. And so that would be 6 divided by 26. And I can fill that in Desmos here in just a minute. And then the C bar for salary is 4,000 divided by 31,000. And then we'll come back and discuss what these tell us about the data. Six and 4,000 by 31. Okay. That means the C bar for age is 23%. We'll round it to. And the C bar for salary is about 13% rounded. So the coefficient of variation is much higher for the age versus the salary. That tells us that the age is much more spread out. The standard deviation is very high relative to the mean. The standard deviation is high relative to the mean. Now, for salary, it's not as spread out. The standard deviation is much lower compared to the mean, which is a good thing. That is a good typical salary then. So using our standard deviation and our mean, we can talk about how typically spread over it. And so we're going to introduce a numerical way to display this bell-shaped symmetric distribution. So we introduced this distribution back in 3.1 and the shapes, and actually the shapes back in chapter 2 when we were looking at our graphs. And there was one that was called the bell-shaped or symmetric graph. And numerically speaking, if our data is and truly bell-shaped or symmetric, then it should fall like this. And this percentages tell us the percentage of the data that should fall within these markers, and these markers are down below. So this is the values of our variable are down along here, okay? And these are the percentages that should fall within there. So this is the mean. Should be about in the center. And then this is subtracting 1 standard deviation, subtracting 2 standard deviations, subtracting 3 standard deviations. And this is if we were to add 1 standard deviation, add a second standard deviation, or add a third standard deviation. So the percentages never change. Those are always going to be the same, but these values down here are dependent upon what topic or variable you're speaking of. So it says approximately 68% of the data is within 1 standard deviation. So if you add 34 and 34, that's 68% of our data should fall between 1 standard deviation value below our mean and 1 standard deviation value above our mean. And likewise, 95% of the data should fall within 2 standard deviations. 99% of the data should fall within 3 standard deviations. This is known as the empirical rule. Okay, we're going to use this a lot for the rest of the semester. If our data is in fact truly symmetric, we call it normal, then our data should follow in this pattern. And if it doesn't, that tells us we have an atypical situation or an unusual situation. And that's going to help us when we start doing hypothesis testing later on. So down below is another picture of how this empirical rule should fall. So typically, if our data is truly symmetrical, 50% of our data should fall to the right and 50% of the data should fall to the left. Now, and that's give or take or approximate, right? It's not going to always be exact that, but that's how it typically should fall. So let's look at an example here. Example 8 says, in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the U.S. is 64 inches with a sample standard deviation of 2.75. Construct an accurate normal distribution with the parameters and percentages labeled. So this is my expectation on the assignments. So the mean is at 64. And then we're going to add 2.75. So 66.75. And then here we're going to subtract 2.75. So let's go ahead and do that in Desmos, and we're going to fill this out. We can fill in our percentages though, because those are not ever going to change. They're always going to follow the same. This should be 13.5, 13.5. And remember, these are percentages, not, so that really, in a decimal form, that's really 0.0015, because that's a percentage of 0.15%. So we're going to take, I'm going to take 64 and subtract 2.75. And then we can do 2 of those. That would be 2 standard deviations away. And that's 3 standard deviations below. So I'm going to fill it out on my on my graph, and then I'll share it with you. So then we can copy those and change those to adding. So once you get those done, you can go back to your paper, and I'm going to show you what it should look like. So this is what it should look like. So these are inches, height in inches. Estimate the percent of women that are between 64 and 69.5 inches. So that would be everyone from here to here. I'm just going to show you here. That would be everyone from within here. 64 to 69.5. So that would be 34 plus 13.5 is going to be 47.5%. Estimate the percent of women that are taller than 69.5. So that would be everyone's taller than 69.5. So that would be everyone here all the way up here. So that would be 2.35 plus 0.15 is 2.5%. Estimate the percent of women that are taller than 64 inches. Well, 64 is right in the center where our mean is, and we talked about how that should be 50% to the right and 50% to the left. So we would expect 50%. Estimate the percent of women that are between 61.25 and 72.25. So I'm gonna mark those 61. 61.25 to 72. So 61.25 all the way out here. So that would be 34, 34, 13.5, 2.35, and 0.15. And that should be 84%. What heights for women would be considered unusual? So to be considered unusual, we're talking about any value outside of 2 standard deviations. And that is shown on your notes on the page prior. And so anything that's considered unusual here, outside of 2 standard deviations above or below. And so anything this way would be considered unusual as well. So if we mark this on here, anything outside of 2 standard deviations is unusual. So if the data truly falls in a symmetric bell shape. So we would say height, so heights that are unusual would be anything less than the 58.5 inches or anything bigger, taller than 69.5 inches will be considered unusually tall. How do we decide what our best measure of center and spread are? And so this is going to be our typical way to decide that. If our data is symmetric, then we can see numerically and on our graph that our mean and our median are about the same. In that case, the mean and the standard deviation are going to be the best measure of center and the best measure of spread. However, if our data is skewed left on the graph or numerically the mean is less than the median, we're going to choose the median as the best measure of center and the IQR is the best measure of spread. And likewise, if it's skewed right, where the mean is greater than the median, notice that it's skewed right because it's pointed to the right, then again, we would use the median as the best measure of center and the IQR is the best measure of spread. So let's look at an example of comparing that. Let's say 2 students, Amy is in algebra class and Betsy is in statistics class. Amy is very happy with her score of 70% on her exam, while Betsy is discouraged with her 80% on her exam in statistics. Why would Amy with a lower score be more encouraged than Betsy with a higher score? Now, I do ask you to answer this in the form in Canvas. I want you to think about what might be going on in the background as we've talked about. Just because of their mean, the average score, how does their score affected? How does that score maybe affected compared to the mean or the standard deviation of the class? So think about that. It's not anything that we know yet. It's just what can we take away from what we've learned in this last 2 lessons to move forward into the next lesson? I want you to think about that. Catch me back for lesson 3.3.